Welcome to the world of PyTorch. In this comprehensive guide, we'll explore the fundamentals of deep learning using PyTorch. Let's dive in and discover how PyTorch can empower you to build amazing AI applications. The slide shows the PyTorch logo, which is a circle divided into two halves with orange and red color, and a white circular tip. So, what exactly is PyTorch? It's an open-source machine learning framework, initially developed by Facebook's Artificial Intelligence Research Lab. PyTorch is known for its dynamic computational graphs, which provide flexibility in deep learning model development. It also offers seamless integration with the Python ecosystem and supports GPU acceleration, making it efficient for complex computations. Here's a simple example of creating a tensor in PyTorch. Import torch. Then create a tensor x using torch.tensor with values 1, 2, 3, and 4. Print the shape of x, which will output 2 by 2. Let's talk about tensors. Tensors are the fundamental data structure in PyTorch, much like arrays, but with added benefits for deep learning. They are multi-dimensional arrays similar to NumPy arrays. Here's how you can create tensors. X equals torch.tensor with 1, 2, 3. Y equals torch.zeros 2 by 3. Z equals torch.ran 3 by 2. The slide also visualizes a three-dimensional tensor with labeled dimensions 0, 1, and 2. PyTorch provides a wide range of operations to manipulate tensors. Here are some common ones. For basic operations, consider A equals torch.tensor with 1, 2, 3 and B equals torch.tensor with 4, 5, 6. Addition. C equals A plus B. Multiplication. D equals A multiplied by B. Matrix multiplication. E equals torch.matmul AB. Reshaping. F equals A dot reshape 3 by 1. These operations allow you to perform element-wise addition, element-wise multiplication, matrix multiplication, and reshaping, among others. One of PyTorch's key features is its automatic differentiation capability, also known as Autograd. It automatically computes gradients for all tensors with requires grad equals true, which is essential for training neural networks. Autograd tracks operations on tensors, builds a dynamic computation graph, and computes gradients automatically. Here's an example. Import torch. Create tensors x and y with requires grad equals true. Perform operations such as z equals x multiplied by y plus torch.power x to the power of 2. Compute gradients using z.backward. Access gradients using printf string dx colon, then x.grad. Similarly, print f string dy colon, then y.grad. The output shows the computed gradients for x and y. Let's build a simple neural network with PyTorch. We'll use the NN module to define our network architecture. Here is an example. Import torch.nn as nn. Import torch.nn.functional as f. Define a class simple nn inheriting from nn.module. In the init method, define fully connected layers. FC1 with 784 inputs and 128 outputs, FC2 with 128 inputs and 64 outputs, and FC3 with 64 inputs and 10 outputs. In the forward pass, apply ReLU activation functions to the outputs of FC1 and FC2, and return the output of FC3. Create an instance of the model. The slide also shows a simple neural network visualization with input, hidden, and output layers, along with their respective sizes. Now let's train our neural network. We'll define a loss function and an optimizer to update the model's parameters. Import torch.optim as optim. Define the loss function as cross-entropy loss and the optimizer as atom, passing the model parameters. In the training loop, iterate over the data loader for each epoch. Perform a forward pass, calculate the loss, perform a backward pass, zero the gradients, compute the gradients using loss.backward, and update the parameters using optimizer.step. This iterative process allows the model to learn from the data and improve its performance. After training, it's crucial to evaluate our model's performance. We'll use a test dataset to assess its accuracy and generalization ability. Set the model to evaluation mode using model.eval. Use torch.nograd to disable gradient tracking during evaluation. Iterate over the test data loader, perform a forward pass, calculate the predicted labels, and compute the accuracy. This process helps us understand how well our model performs on unseen data. Key aspects include setting the evaluation mode, using performance metrics like accuracy, disabling gradient tracking, and evaluating on a separate test dataset. Saving and loading models is essential for reusing and deploying our trained models. We can save the entire model, or just the model's state dictionary. To save entire model, use torch.savemodel to model.pth. To save model state dictionary, use torch.savemodel.stateDictionary to model_state.pth. To load entire model, use model equals torch.loadModel.pth. To load state dictionary, create an instance of the simple NN model, and then load the state dictionary using model.loadStateDictionary, loading model_state.pth. Saving just the state dictionary provides more flexibility and better compatibility across different environments. Congratulations on completing this introductory guide to PyTorch. There's still much more to explore in the world of deep learning. For advanced topics, delve into convolutional neural networks for image processing, recurrent neural networks for sequential data, and transfer learning for quick model deployment. Make use of the official documentation, community forums, and example projects to enhance your learning experience. Keep practicing and experimenting, and you'll become a proficient PyTorch user in no time. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.